store parameter. But if there's somebody who needs to play with it and wants to try it, come and ask me. Percent free. This is becoming a lot more important, I find, with Java apps. We have seen a pattern of people writing Java apps that write a row out with all nulls and then go back and fill all the nulls in. It plays havoc with Oracle performance. Oracle was not designed to work like that. If you're doing that, you need to leave an awful lot of space on the block in order to have to go back and fill in those values. And there was an additional problem that we had, which was before 12.2, if you updated any nulls above column 255, it created a new row piece in a different block. I saw somebody do a test case in their blog where they successfully updated columns 256, 257, 258 and managed to get one column on each of 50 different blocks. Which is why updating null rows, trailing nulls, can be painful. 12.2 has been changed to try and keep everything on the same block. So try and avoid that particular style of Java programming, but if you're going to use it, make sure you have left a lot of free space at the beginning and that percent used, you don't want that block added to the free list because you want it to remain available for updates to rows that are already on that block. If it gets added to the free list, new rows might come in and try and use space on that block. So, we talked about this. So, this is one of the issues to be careful of. So, what can you do about it if you have a segment that has become very highly fragmented? Well, there are two options. One of which is to set row movement enabled, alter table enable row movement, and do alter table shrink space compact as an online operation, which has to be followed by a shrink space. If you're on Exadata, this statement did exactly the wrong thing for Exadata performance, because it gathered all of the head pieces together and then gathered all of the last pieces. If you have enough space and cycles, alter table move will relay the partition down in a perfect layout. It is puts everything back into an optimal pattern for performance. If you have the space to do it, because it means briefly there are two copies of the data, and you have the CPU resources to do that. And if it's become a cold segment and you're on Exadata or ZFS, or data warehousing cloud service, you can do compress for query to repack it and get it compressed. If you don't have disk space, you can do a data pump export and a data pump import. Because the data pump import will do a direct path load, which will also put things down in an ideal order. Chained rows on Exadata. Is anybody here on Exadata? Okay. Chained rows create a particular issue for Exadata. Exadata works by looking at data 1 megabyte at a time in SmartScan. It can only process chained rows if all of the chain pieces fall within the same 1 megabyte. Otherwise, it has to return the row to the database for the database to use the NRID to go and do a buffer cache get of the block the row piece it doesn't have. We made changes in 11.203 so that loads would always align on 1 megabyte boundaries. We've made a lot more changes in 12.1 and 12.2 for how we search for space when we're doing updates to try and keep things on the same block, or if we can't, to keep them within the same 1 megabyte region. Row major data we will only offload up to 255 columns. Up to 12.2, I don't know if people look at block dumps, there was a special row piece called an N row piece that was very rare. It's if you updated a column to be too wide that we'd end up wasting space, you could actually split a row piece in the middle of a column, and it's called an N row piece. And before 12.2, Exadata didn't process N row pieces. And prior to 12.2, all of the chained row pieces had to fit within the same block size as the input block, and that has been lifted as well. For row major, we'll now return 32K blocks if needed. If you want to look at the stats, table fetch continued row. If you're getting very high numbers here compared to table fetch row, then it indicates, you need to look at what's going on with performance and how you're managing space. Exadata has 3 steps for following. Chained rows skipped by a cell, meaning we didn't have all the row pieces we needed. Chained rows processed by cell means we did have all of them, and rejected by cell means we couldn't find enough output space to return that row after we stuck all of the chained row pieces together. So let's go on to scanning in memory. Just kind of basic refresher. Databases, when they were first designed, the huge problem was disk I/O and locking. Databases were designed to get in and out with the smallest possible disk write and the briefest possible period that a lock was held. 2K blocks, not many indexes, and everything was designed to make sure that the writer, the person writing or changing data, had absolute priority on how the system worked, and queries were something that followed on behind and got resources and whatever performance was left over. And then came data warehousing databases, which is where I started, where we threw it all away and went in completely the opposite direction. They had small pages, we had big ones. They had data in rows, we had it in columns. They had many indexes, we had few. They typically had short transactions, we had long, etc., etc. And row major databases need workarounds for data warehousing queries, and column major ones needed workarounds for row inserts. I spent 10 years as the query engine architect for the first commercial columnar database. And then I got frustrated because row major on its own had problems, column major on its own had problems. We needed both. We needed transactions to run fast and data warehousing to run fast. And as you've probably heard from too many people already, Oracle is unique in offering both at the same time. I'm not going to repeat all of that. I just want to talk about performance of table scans within memory. So the first thing is it completely in memory? So bytes not populated in $IM segments will tell you if it's completely in memory or not. So it's completely in memory. But if I now do some DMLs to a table that's in memory, I'm now going to change the performance, because the row in the columnar store is now invalid. So what we're going to do is we're going to change a bitmap that says row 57, you can't use it from the in-memory store. And we will run the query against the column store in memory. We will X out the results for row 57, and then we will go to the buffer cache to get row 57. Now, if row 57 has just been updated, it's probably still in the buffer cache. So it should not lead to a disk read. And that is the idea of the design. if you want to track, and then